High-speed trains are, of course, marvels of engineering, but just as crucial as making them go incredibly fast is figuring out how to make them stop. So let's dive into the amazing, multi-layered technology that brings hundreds of tons of steel to a safe halt from speeds over 300 kilometers an hour.
Come on, we've all seen it. That big red handle. The sign says emergency use only, but that little question always pops into your head. What would actually happen if I pulled it? Well, the answer is a lot more complex and way more interesting than you probably think.
So yeah, let's start right there, with that famous red handle. What a lot of people don't realize is that its job has completely changed over the years. It's evolved from a simple brute force switch into a really sophisticated communication tool. And that change tells us a lot about how we think about railway safety today.
And right here, this is the crucial difference. The old school cord was, well, a blunt instrument. You pull it, and the train screeches to a halt, no matter where it is. I mean, just imagine stopping dead inside a narrow, dark tunnel. Not ideal, right? Today's PASCOM system is much smarter. It's not really a brake lever anymore. It's more like a help button. It sends an alarm straight to the driver, who then gets to make a critical call. Is it safer to stop right now or to keep rolling to a station or a safer spot? It's all about giving the expert in the cab the context they need to make the best decision.
You know, the old system was brilliantly simple, really. It was built on a fail-safe idea. See, the brakes are actually held off by constant air pressure in a pipe running along the train. So pulling that cord just opened a valve. All the air would rush out, and with no pressure left, boom, the brakes would slam on. It's effective for sure, but it's a total all-or-nothing approach that takes all human judgment out of the picture.
Okay, so let's move from the passenger's help button to what's happening up in the driver's cab. For the driver, the emergency brake means something completely different, and using it comes with some really serious consequences.
So this is the key. This isn't just, braking a little harder. When a driver goes into emergency, they are unleashing every single ounce of braking power the train has. It's an abrupt, violent maneuver that they will do pretty much anything to avoid.
And this is why it's a last resort. An emergency stop is a brutal event for the train. It can literally grind flat spots onto the solid steel wheels, which is, as bad as it sounds. It can even damage the track itself. And it triggers this whole cascade of automated actions. Power gets cut, sand might get dumped on the rails for grip, the horn just starts blasting continuously. It will stop the train, but it definitely leaves a mark.
So this brings us to a really fundamental question of physics. You have all this forward momentum, a 400-ton vehicle moving at incredible speed. That energy has to go somewhere, right? It has to be converted into another form of energy. The answer? Heat. An absolutely colossal amount of it. We are now entering the world of some pretty extreme thermodynamics. See, the challenge isn't just stopping the train, it's designing a system that can actually survive the inferno that gets created in the process.
And this right here is where it all happens. You're looking at these huge cast steel brake discs. When the train needs to stop, brake pads squeeze down on these discs, and the resulting friction is what converts all that kinetic energy into thermal energy. Simple principle, but the scale is just immense.
And when I say immense, I am not kidding. This thermal simulation shows you just how intense that heat gets. The surface of the disc, right where the pads make contact, can get hotter than a commercial pizza oven. We're talking glowing red hot in just an instant.
And to put a really precise number on that glow, we're talking a peak temperature of over 350 degrees Celsius. That's nearly 700 degrees Fahrenheit. So the real engineering challenge isn't just stopping, it's managing that thermal shock so the entire disc doesn't warp, crack, or just completely fail.
So how do they do it? Well, the solution is just brilliant. The disc itself is designed to act like a giant centrifugal fan. As it spins, those 72 channels you see on the inside, they grab cool air and force it right through the core of the disc, actively pulling all that destructive heat away. So clever.
So far, we've talked about human actions, pulling a handle, and mechanical reactions, discs getting hot. But in the world of high-speed rail, the biggest dangers are often invisible. They happen faster than any driver could possibly respond to.
And that's where the third layer of safety comes in. Think of it as a digital co-pilot that's always watching, always calculating, and always ready to step in. This is the Automatic Train Protection System, or ATP.
At the very heart of this digital guardian is something called the ATP protection curve. Now, the easiest way to think about it is as a moving safety bubble that's always projected out in front of the train.
The system uses data about the track ahead, curves, signals, other trains, and it's constantly calculating the absolute maximum speed the train can be going at any given moment and still be able to stop safely. If the train's actual speed ever touches the edge of that bubble, the system intervenes. So the ATP's job is relentless. It's always monitoring the train's speed and exact location. It's preventing collisions, it's protecting against going too fast into a curve, and if the train's actual speed even gets close to that calculated safety curve, the system takes over and applies the brakes itself, automatically. It really is the ultimate failsafe.
And this digital guardian isn't just flying blind. The train is in constant, real-time wireless communication with the track and a central control system. It's basically shouting out its exact position and speed second by second. This creates this incredible network where the whole system knows where every single train is, allowing those safety bubbles to adjust on the fly for a super safe, seamless flow of traffic.
So, let's bring it all together now. Stopping a high-speed train isn't about one single system doing all the work. It's really a symphony of human oversight, powerful mechanics, and a digital co-pilot, all working in perfect harmony.
This table, wow, it really puts the physics into perspective. At 100 kilometers an hour, it takes about the length of 2.5 football fields to come to a stop. Okay, now at 160, the distance more than doubles. But look at that top speed. To stop from 300 kilometers per hour takes nearly 2 kilometers. That's over a mile. It is a staggering distance that just shows you the colossal energy these systems have to absorb.
So you see, the whole thing is about layers of defense. The passenger has a voice, the driver has ultimate control, but with serious consequences for using it rashly. The mechanical brakes are there to absorb unbelievable forces, and that digital guardian is always there, watching over everything, making sure the laws of physics are never, ever broken. It's this combination that makes these trains so incredibly safe.
Which leaves us with one final interesting thought. In a future where trains are fully autonomous, where an AI is always making the perfect, safest decision, does the passenger need a say at all? Or is that simple red handle a connection to human control that will just never be ready to give up?